everyone. So I am a current PhD student working out in Australia, but for the past 3 years I've been working at the Lethbridge Research Centre with Agriculture and Agri-Food Canada. So today I'm going to be talking about reductions in livestock emissions, focusing on ruminants and mostly beef. So I'll give an overview of our current statistics, look at some factors which affect methane emissions in ruminants, and then look at some future research that has been happening. Thank you. So looking globally, the contribution of agriculture to greenhouse gases varies from country to country and is largely dependent on the structure of agriculture there. But looking at animal agriculture specifically, on a global basis, it accounts for about 40% of agricultural-based emissions. And about 30% of this comes from animal management and another 30% from manure management. So two gases that we look at when we talk about ruminant production are methane and nitrous oxide. Methane comes from enteric production, so directly ructated from the rumen of ruminants, and manure. Nitrous oxide has lots of different components related to agriculture, but about 40% of the nitrous oxide comes from direct excretion from the animal. So when we talk about methane and nitrous oxide, we talk about them on a global warming potential. So essentially, carbon dioxide has a global warming potential of 1, and this is related to heat trapping over a 100-year period. So methane has about 25 times the global warming potential of CO2, and nitrous oxide has 298 times the global warming potential of CO2. I know in ruminants, when we're looking at greenhouse gas production, there's definitely a lot of neglect when we focus on greenhouse gas emissions, as we usually focus just on methane, but purely just because of the intensity of the potency, I guess, of nitrous oxide, it's important to consider both of these factors when looking at dietary mitigation of methane. So looking at Canada's greenhouse gas production, so this is from 1990 to 2016. So as you can see, overall production of greenhouse gases has increased since 1990. However, when you look at agriculture, whilst there was an increase in total gas production since 1990, it has actually remained relatively stable since about 1994. So in 2016, beef production contributed about 2.4% of total greenhouse gas emissions, which equates to about 23.4 million tonnes of greenhouse gases. This is 30% of Canada's national methane emissions and about 77% of Canada's national nitrous oxide emissions. And from this methane emissions, about 41% of this derives from enteric production. However, when you look at this back on a global scale, Canada's doing very well. So overall, agriculture contributes about 8%, but when you look at beef production, it's only 2.4%. And when you look at total beef production related greenhouse gases, it only contributes about 0.04% of global greenhouse gas emissions. So whilst there has been an increase since 1990 of greenhouse gas production from beef sectors, there has actually been a decrease by 14% in greenhouse gas emissions per kilogram of live weight. And as identified just previously, this is a really important factor to discern from. So whilst production of greenhouse gases on a total basis has increased, the intensity at which we produce greenhouse gases from beef production has actually decreased. And this was so this graph actually shows in Australia, Canada and the US, and all of them have said a similar reduction rate. So, though we did have this 14% reduction in greenhouse gas emissions intensity from beef, there was actually the same amount of beef produced as 1981 as in 2011. And I know this statistic is a little bit old, but it's a really nice number. So the two main reasons why there was this decrease in greenhouse gas emissions intensity was the shift to more animals maintained on high-grain diets, as well as improved reproductive performance. This increased average daily gains and increased slaughter weights, which in turn reduces the time it takes for that animal to slaughter, and as well gives the farmer the ability to market cattle at a younger age. So Canada has improved its animal-related emissions by improving productivity. But as you know, there is a long way to go. The world cattle population is estimated to double by 2050. And whilst domestically beef production demand may remain stable, North America will play a vital role in exporting beef for the global increase in population. So back to the basics of how methane is produced. So the rumen harbours a unique population of microbes. So this big fella here is a protozoa, the little guy on his side is a fungi, and you've got archaea and bacteria, which is colonising the bottom of it. So protozoa, fungi and bacteria all play an important role in the degradation of feed which enters the rumen. Archaea, however, have a special role in the rumen in which they convert hydrogen and CO2 into methane. So essentially the process for this is that feed usually consists of starch, cell wall polymers or fibre, and protein. And these are degraded into either simple sugars or carbon skeletons. These in turn go to produce volatile fatty acids, which provide about 70% of the animal's energy requirements. So the three main types of volatile fatty acids produced in the rumen include acetate, butyrate, and propionate. So the importance of this is that acetate and butyrate in their synthesis actually produce both hydrogen and CO2, whereas propionate in comparison actually utilises full hydrogen. And as I mentioned before, it is this hydrogen and the CO2 that is produced in the obtaining of these volatile fatty acids that the methanogens use, or the archaea, use to produce methane. So there are many factors affecting greenhouse gas emissions from ruminants. The number one determinant is dry matter intake or feed intake. So this is two graphs plotting dry matter intake on the bottom in kilograms per day versus methane in grams per day. On the left we have dairy cattle and on the right we have beef cattle. So each of these individual dots represents a study that has looked at trying to represent the relationship between how much an animal is eating and how much methane is produced. And as you can see, there is a huge variability even at the same level of intake. And this is mostly due to diet composition. So one of the big factors which affects methane production in the rumen is starch content and total diet degradability. So feed type is the biggest one. So grains will produce less methane than forages. Even within grain type, wheat has been shown to have less methane associated with it than barley, and then that of corn. Similarly, the processing can also affect this process. So cracked corn will have less methane associated with it than steam flaked. And essentially this comes back to the easiness at which the diet is degraded. So essentially, the quicker that the feed is degraded, the less methane is produced from that associated feed degradation. Because when you have a more fibrous feed, it takes more of these microbes that I talked about before to degrade that feed. Another reason why increasing the degradability can reduce methane emissions is that you get a lower pH. And essentially that's because you're getting an increase in production of these volatile fatty acids. This lower pH can also result in decrease in the growth of the methanogens, as well as protozoa and fungi. And these protozoa and fungi are known to be big hydrogen producers and are very important in fibre degradation for this reason. Increasing total digestibility can also increase passage rate, which I'll talk about a little bit later, and also increase propionate production. which, as I mentioned before, utilizes hydrogen in its synthesis. However, looking at studies that have looked at the effect of grain concentration on methane production, concentrates only reduce methane when given at over 80% of total dietary dry matter. Additionally, supplementation with grain can actually increase methane, because once again, you're getting an increase in overall production in the rumen. However, this is still decreasing greenhouse gas intensity, so it's still a positive outlook. One kind of disadvantage with this is that if you are supplementing grains at a high percentage, you can get a decreased pH, which leads to rumen acidosis, and essentially you're affecting the ability of that rumen to produce, deposit meat. So this can increase your greenhouse gas intensity. So anything that's going to alter the optimum performance of that animal is going to increase your greenhouse gas intensity. So as I mentioned before, forages or NDF can play an important role in methane emissions, and once again, legumes have been associated with less methane than grass, cereal silages less than grass silages. And once again, this is the ability and the time it takes to degrade this feed. Something else that has been of important interest, I guess over the past 15 years, has been condensed tannins contained in legumes. So I know two Canadian tannins, which are found in pastures here, include the bird's foot trefoil and the sandfoin. So back in 2004, they found that in dairy cows, methane was decreased by 14% when bird's foot trefoil was included in the pasture. It also increased milk intake, milk yield and milk intake, and also has the added advantage of not causing bloat. In contrast, the sandfoin has had very variable responses in methane mitigation potential. So some studies have shown increases, no changes, or decreases in methane mitigation potential. Once again, the increases in dry matter intake have been seen and digestibility, but also decreases. And one important thing when we look at saponins and tannins is that they can have inhibition of NDF or fibre digestibility, which does essentially decrease methane, but you're also decreasing the availability of nutrients to that animal. So obviously it's not favourable. And a lot of dietary additive strategies, generally when they're given above a certain level, do cause a depression in fibre digestion, which is obviously counterintuitive to what we want. So some of the other issues with tannins is that there are such a vast different types of tannins, which there's over 200,000 different phytochemicals that are obtained within different plants that have these tannins, and their effects on their concentration in the diet can alter how they affect rumen digestibility. Another thing with tannins is that they may also decrease crude protein digestibility. And essentially these tannins form complexes with protein, and I guess the idea of them is that they're supposed to form complexes in the rumen, and then once they reach the abomasum, which is the human equivalent to a stomach in a cow, they dissociate, where the protein can be directly utilised. However, this is not always true, and this can be seen by the decrease in crude protein digestibility seen with many of these trials. However, this can also be a positive thing when we're looking at nitrous oxide emissions, because they can increase fecal nitrogen in place of urine nitrogen. And urine nitrogen is a lot less stable in the environment and has higher nitrogen-related emissions. So another dietary composition that we can alter is fat content. So this is a graph plotting methane production on a gram per dry matter intake basis on total dietary fat content. As you can see, it's a very nice linear equation here. But essentially, as you increase the total dietary fat content, you're going to get a decrease in methane production. However, there is restrictions to this. So there is a high cost of lipid supplements. Essentially, you can only add, it says 6%, but it's about 6.5% of total lipids in the diet, which is about 2% added on an as-fed basis. and levels beyond this can decrease fibre digestion as well as depress milk fat content. So looking at this 6.5 addition of fat can result in optimally about a 10 to 15% depression in methane production. However, this is highly dependent on, once again, the type of fat. So 3 reasons why fats may reduce methane in the rumen is that it may have a direct toxic effect on methanogens, as well as these high hydrogen producing protozoa. They also replace fermentable carbohydrates and are a direct energy source. So essentially you're almost diluting the availability of substrates to degrade, which produces that methane. Another one is they provide an alternative hydrogen sink by bihydrogenation of the fats. However, I don't really, this is only being shown to represent about 5% of hydrogen sink pathway. So looking into more dietary additives now, there's many different types. So tannins I've already mentioned, essential oils, organic acids, probiotics, enzymes, and prebiotics. So there are a vast variety of the methane mitigation effect. So 3-NOP, which I'll mention in my next slide, has a high mitigation effect. Tannins and saponins have low and variable, whereas dietary lipids, inclusion of concentrates, and improving forage quality can all have a low to medium effect. And those 3 are mostly related, well, the bottom 2 are mostly related to improving the greenhouse gas intensity, more than actually decreasing the production of methane. So one additive is 3-nitrooxypropanol. And this is a compound which actually directly inhibits the enzyme activity in archaea. So they don't actually depress the amount of archaea that are in the rumen, but they actually inhibit their activity. So there was found to be up to an 80.7% decrease in methane when animals were given 3-NOP. This is also a nice linear relationship, so when you increase the amount of 3-NOP in your diet, you usually get a linear decrease in your methane production. This has been kind of investigated over the past 10 years, but it's not yet improved in Canada or the US, but I know they're definitely looking into that now. There needs to be more research on it, definitely, because one of the things as researchers in ruminant nutrition, especially when you're looking at greenhouse gases, is that they say that methane eructated from the rumen accounts to about a 2 to 12% loss in gross energy intake. Whereas most of the time, a lot of these additives, when we have seen these big decreases in methane production, we haven't actually seen an increase in performance-related parameters observed with this additive. So something else that has had renewed interest, I think even just within the past few years, is using seaweed or algae. So preliminary studies have indicated in the lab or in vitro that methane was reduced by up to 40% without impacting any of the gas production or lab parameters which we look at. This seaweed asparagopius, or red algae, was actually also found in the lab to decrease methane production by almost 99% when included at only 2% organic matter. So this same red algae was introduced into sheep in Australia, and they found that also there was a 63% reduction in methane, and that was in 2018. Similarly, there's been down in the US some studies looking at it in Holstein cattle, which have found about a 60% reduction in methane production. However, this study has not been released. So there are several issues with this as a dietary additive. I know with the sheep study, and I'm not 100% sure with the dairy cattle study yet, but there was reports of decreased dry matter intake. And this may be due to the inhibition of fibre digesting in the rumen, which essentially makes the animal feel more full, which means they're not going to have as much intake. And this can also be seen through a decrease in volatile fatty acids. These chemicals within the seaweed may relate to tannins or chlorotannins, which is specific to marine algae. They may also have anti-methanogenic properties, so they may inhibit the activity of archaea within the rumen. I know this red algae one concern is that it contains bromoform, which is a carcinogen, so it may not be safe to be given to animals. So some future things that we need to look into is the rumen microbiome. So several times when we use dietary additives is that when we first start including it, we get a good reduction in methane. However, in the long term, the rumen microbiome actually adapts to this feed additive and goes back to producing the same amount of methane as it did originally. So long-term studies need to be looked at. I know the sheep study looked at the haliforms and they found that they were not deposited in meat. However, this also needs to be looked at in beef cattle and dairy cattle as well, and just checking for a variety of potential toxins that could affect their use in agriculture. So we also need to look at long-term health effects of feeding this additive to cattle. But as I said, there's limited studies and it's a new area of interest, so there's a lot of work still to be done. So also just mentioned, so breeding programs has been talked about to essentially use genetics to find and produce a population of low emissions of cattle. So methane production is actually a relatively heritable trait, and this was found in sheep, I think, as well, but they've also done studies in cattle. So the number one determination of methane production is microbial abundance and expression, and this is of the archaea. However, low methane yield rumen has also been associated with the heritable trait of methane output. So a smaller meat rumen essentially means that you're going to have a shorter retention time of feed within the rumen. This will give less exposure time of the microbes to the feed and then give you less methane production associated with it. Alternatively, if you have a large rumen, you're going to have a longer retention time, more exposure to the microbes, the longer time it takes them to digest, and then you're going to get more methane produced as a result. So there has been a found correlation between methane yield, retention time, total feed, and rumen volume. Additionally, low residual feed intake, so essentially that means is that we look at how much the animal is actually eating versus how much we predicted them to eat. And essentially, the lower that number, the more efficient that animal is. So that has been associated, low residual feed intake has been associated with more feed efficiency and lower methane production. However, back again to fibre digestion, a decrease in methane production has been once again associated with a decrease in diet digestibility and fibre digestibility. So the important thing with all these things is that we need to find a balance. Like the fat, we have kind of found that balance of 6.5% is the level, the maximum level that we get a maximum reduction in methane without altering fibre digestibility within the rumen. So, though we've been looking at methane mitigation in ruminants for quite a while now, we haven't actually found any amazing solution to the problem. So I think the best way today to decrease methane related emissions is to improve the efficiency of production and reduce the days until slaughter and reduce the number of animals required to produce the same quantity of beef. So it's all about improving the efficiency. I think there are several products that I've talked about today that may have potential in the future. However, these products are not available at the moment and take years of studying to be able to implement within industry. And additionally, the biggest issue with a lot of these things is that who pays for it. So with the 3-NOP, if there's not going to get an increase in production, but it's going to have a huge reduction in methane, then who actually suffers from that cost? So another thing is that a lot of these recommendations that I talk about take away from the fact that ruminants, the reason we use cattle is that they can effectively turn fibrous and recalcitrant matter that no other species can use into product that we can use. So I've talked about, increasing concentrates, but that's just not viable. We can't just say, let's just move all cattle into a high concentrate diet. It's not going to work. So something that we really need to focus on is improving, I think, fibre digestion within the rumen. Whereas a lot of these strategies actually take away from that. Then altogether, there is a complex process and there's no easy fix at the current moment. Essentially, best management strategies and improving your overall efficiency. So, which I think is what most farmers are aiming for anyway. So that's kind of a nice way to achieve both of those things. So, and that's all. Thank you.
Okay, questions?